Welcome, legends. This is Mr. Maze coming to you through the digital gate. It is a pleasure to have you here. And as you can see, we're going to be doing Unit 2 Pro Tips. Don't forget to smash that like button and annihilate that subscribe key or whatever it is. I forget. Press the bell. I'm joking on all of these, of course. And I want to start us off with these 3 questions that I have from the show with hot questions. You'll remember this for those of you who made your way to my station. I think it was Station 5 in the Stat Olympics. Thank you for rolling through the Stat Olympics with me and enjoying the chaos and the wonder and the horror that befalls us all when that many people are trampling about in a classroom. I had an immensely fun time, and I hope you learned a thing or two about trying to employ stats under very tense circumstances. Now, all of that said, let's go through these 3 questions in depth. These are all 3 phenomenal questions to prep you for the kinds of stuff you're going to see on the Unit 2 exam. So, of course, I had to add them to the Pro Tips video. They're also good critical thinking questions. So let's roll ever forward. I want you to take a second and read question 1. Go ahead and pause the video. And you should have had it unpaused at this point, so you know what the question is. You've maybe picked an answer, I hope. And, of course, the answer for this one is going to be an experiment with a completely randomized design. Now, the main mistake people make with this one, you might be unsurprised to hear, is either they mistake it for a matched pairs experiment because we have 2 batches of guitars getting 2 different treatments, but we have not actually paired guitars up based on similar make. Now, if we did say guitars were paired up based on whether they were similar body shapes or similar lacquer types or something like that, that would be a matched pairs experiment, but we didn't do that. Another mistake people sometimes make is that we blocked, that we blocked based on polish versus no polish. Now, wisely, you're aware that those are not block types, right? Now, this is an experiment, so we are blocking, we're not stratifying, but we aren't going to block based on polish because polish is not a quality of our subject, of course, being the guitars. No. These are treatment types, and we're only using one factor, right, for our treatment, and that is polish or no polish. So if anything, you would argue that no polish was the control group and polish was the treatment group with only one treatment factor available. So it was not a blocked experiment, and for that reason, we choose a completely randomized design. You should also know this isn't a census. You have to interview people for a census. So hopefully that was pretty clear. And we are rolling on to number 2. Take a second, pause the video, read the question, and pick some answers. Okay, you should have paused and picked your answers, and let's take a look. For part 1 of this, offer me an example of sampling or selection bias. It's really important that you know, for any type of problem that you see, that the 2 main kinds of bias you have are sampling selection bias or response bias. Overall, they are the most common ones you will pick an answer for. You should also know that sampling or selection bias has to do with the people you initially bring into your survey. So in this case, it says a recent poll of 3,000 people. They don't give any details except that they are from across the 50 states. Now, that's pretty good. The problem here is they don't state the age ranges. And this question is about voting. So a kind of sampling selection bias you might offer, mind you don't have to name it, is you could just say, hey, we might have underrepresented. It could have been underrepresentation bias. You just said, hey, we might have underrepresented a particular subgroup of people. We might have only interviewed people, between the ages of like 50 and 70 in that 3,000 person cluster, and we might have made that mistake, right? You could have also said we accidentally interviewed children who are not able to vote, right? Okay, so that takes care of our sampling or selection bias question. The second one, and this one's super important because I really want to highlight this because this mixes people up sometimes. Excuse me, big burp. This is after I've eaten all this hot sauce, so bear with me and my gastrointestinal tract. Offer me an example of response bias. In this case, the big response bias you should get to is people do not want to admit when they don't vote, right? So that is a kind of social desirability bias. So be aware that anytime you have a particular survey question or a sample that you're toying with, and it becomes very clear from the question, oh, hey, we're not getting the right details. Now, obviously, we don't get the rest of this. We don't find out if the final amount of voters ended up being much lower than expected. But for example, if it were, we would know response bias was at fault, right? People did not want to admit to not voting, and that was a frailty of the actual setup, right? A response bias issue. This actually is pulled from Georgetown University, where they're doing some really cool studies, and I'll talk about this later on in the year, but they're doing some really brilliant statistical analysis on how comfortable people are with voting and admitting they're voting. It turns out a lot more people are uncomfortable voting than you would imagine, and obviously a lot more people are uncomfortable admitting that they do not like to vote or do not feel comfortable voting. Okay, hopefully those make good sense. Now we go on to question 3. Take a minute, pause the video, and pick an answer. And you should have paused the video and picked an answer. And from what we're seeing here, I'm actually going to start writing out some responses here. Ooh, I'll set up two little tick marks here. The 2 things we are asked for here is the type of study and the response variable. Now be clear here. When we say type of study, we are asking, is this an experimental study or an observational study? And you should have gotten that this was an observational study. Now I like this one. 1, because clearly I wrote it with my very bizarre jargon of writing, but 2, because an observational study in this case looks very scientific, right? And observational studies are very useful and very scientific. However, you will note no variables have been changed, and this is very important, in observational studies, we do not randomize treatments. In experiments, we do randomize treatments. So one thing to keep very close note of, observational study, no randomized treatments. In this study, they did do a great job of going to every single floor. And if you made the mistake of feeling this was an experiment, you might have said, well, they blocked based on floor level, and that would be true if it were an experiment, but they didn't actually run a treatment of any kind. There was no randomization either, except maybe that they said they took 6 measurement readings from the first floor, but it didn't say if they were randomized. Ostensibly, they were, right? But for these reasons, we should know this is an observational study. Wonderful, wonderful, wonderful. You can hear my little guy joining us in the fun. Okay, now on top of that, it also asks, what was the response variable? Super important to be able to identify this. In this case, it was the plasma count. I'm obviously making up what a plasma count is. I also don't know if that's actually how fake ghost searchers or ghost hunters determine if samples are there or not, but they're looking for plasma count. Remember, the response variable is always, always, always the thing that you are anticipating, normally called the dependent variable, right? You should get that from previous video notes. Just normally it's the thing that you are looking for that you will get if your initial condition is true. So normally, right, the initial condition is the explanatory variable, aka the factor, right, in that case. So in this case, the factor was, ghosts being present, and the response variable was plasma being present there, right? We had to see plasma for ghosts to be there. So that's explanatory variable leading to response variable. Okay, now that's a great way to shoot us into my pro tips for you for Unit 2. So let me just write that down. Unit 2. These are the mega pro tips. Now that we've moved beyond the questions of these recurring. Endless cities of the faithless. Cities of the foolish. Something like that. I can't remember. What good amid these, O me, O life. Walt Whitman. Okay. One thing you should be very, very clear on is you should know what experimental units are. You should know that the experimental units are normally called the subjects if they are people, right? You should know that they are the thing the study is about. Make that A a little clearer. Okay, that is the thing the study is about, the experimental units or subject, right? Second thing you should be very clear on, I just went over this a moment ago, but explanatory variable. AKA the independent variable, right? The one that we, the researcher, are controlling in an experiment, right? Again, all of this is for experiments. And that explanatory variable, you should also understand how it relates to treatment, okay? Now, the treatment is the mix, and we normally, of course, call the explanatory variable the factor. And the factor, aka the explanatory variable, often has levels. This is all review from old stuff, but you should know that those levels in that factor always enhance our understanding of the treatment. And the treatment groups, or the treatments, are just the various combinations of factors and levels that different patients get. Side note on this, and this is a super important thing to have drilled into your skull. I'm going to call this the side note. But you will need this, so do not forget this. When we are looking at explanatory variables, aka factors, remember it's the same thing, that have levels, be aware that we sometimes have 2 explanatory variables that we're toying around with. Therefore, we have 2 factors, and those have multiple factor levels. So an example I want to give you is I want you to imagine that we have a group of people we're randomly studying who are having allergic reactions, okay? Which is a horrible thing. Now, I want you to imagine that we're doing the following thing. We have 3 different corticosteroids. And I always forget how to spell corticosteroids. I hope it like comes to me. I think it is corticosteroids. Well, if I misspell it, say Levy. So imagine for a second, right, that we have these particular kinds of corticosteroids, right? And those 3 corticosteroids come in 3 levels of strength. Right? So now we have 3 kinds of corticosteroids, right? Which is an explanatory variable, 3 different ones, and we have 3 levels for each one of those corticosteroids. Now, when I say what's the treatment, a lot of times people, especially in class, have asked me, hey, like, Mr. Mays, you don't understand, what's the difference between treatment and factor or treatment and explanatory variable? And here you'll see. The explanatory variables are the corticosteroids and the levels of strength. The treatments are, or the treatment groups are, steroid 1 at 3 levels. Right? So let's say steroid 1 is called steroid A. Steroid 2, steroid B, and steroid 3 is steroid C. Each one of those has 3 levels. That should make sense, right? What that means is that we actually have 3 times 3, 9 different treatment groups, right? So let's say the 3 levels of strength that we have are moderate. I'm remembering moderate to severe ulcerative colitis, if I made that joke in your class. Moderate, severe, and normal. No, I guess normal sounds like moderate. Let's do low. I'll be mid. Let's do low. Okay. So we have low, moderate, and severe, and we have A, B, C. That means our 9 treatment groups are A low, B low, and C low. A moderate, B moderate, and C moderate, and A severe, B severe, C severe. Now, this is a lot of fancy garbage I'm throwing your way, but all that this should come out to for you is naming the different treatments is just a matter of taking your factors and multiplying them by the number of sub-factors we are working with or levels we're working with, right? If we have 3 steroids we're trying on patients at 3 different strength levels, we are actually trying 9 treatment groups, right? And you would list those out. Okay, so we've gone over explanatory variable, we know factors, we know the levels, we know treatments, and we know the different ways in which we might enumerate those treatments. And you definitely will have to do something like this on my exam. Remember also, and this is moving back into our basics, the response variable, I already went over this, we just tried it out, but just be very clear that the response variable is also known as the dependent variable. It's the output, it's what we're watching, it's what we're studying to see the impact related to, right? We want to see how this responds in our subjects given the changes we made to treatment or to control. Okay, and very, very key here also is make sure you know sample versus population. Now, this might be very obvious, but again, sample is actually the group of people that we are studying, and the population is the thing we are generalizing to. And make sure you know generalization. We went over this in class, but generalization is the degree to which we can take our research and apply it to a grander or a greater scale, right? When we do sampling methods, and surveys and things of that nature, as long as we randomize effectively using the different randomization methods, the different sampling methods, we can generalize to the subgroup we are studying, right? The thing I was just saying to you guys, excuse me again, is if I'm, doing surveys and I do smart stratified random sampling, for example, to groups of high schoolers in Alexandria at Alexandria City High School, and I do my survey well and I run my sampling method correctly, I can generalize to all high schoolers who meet those criteria at Alexandria City High School. On the other hand, with something like an experiment where it's randomized, I may not actually be able to generalize it that far, but I can prove causation, which is really exciting. But we'll go more into that in a moment. Okay, so we've gone through all of those categories having to do with experiments. And know, of course, to name all your treatment groups. We went over that as well. All right. Know the difference between an experiment and an observational study. We went over this already, but I'll pull back up really quickly. Remember that observational studies have no randomized treatment groups versus experiments do have randomized treatment groups. Yes, indeed, they do. And remember, of course, that an experiment, no matter how bad, an experiment, and we went over this in class, always shows causation. That's why they're useful, mind you. That's why we do them even when we can't generalize experiments. We talk a lot in class about how, oh, we did this particular experiment or we looked at this particular experiment and I can't generalize it. Why would I do it? Well, I would do it because it can show some kind of causation between my explanatory variable and my response variable. On the other hand, observational studies only show correlation at best. Okay. Wunderbar, as they say, for my German compatriots. Okay. You must know the 4 most important parts of experiments. When you are analyzing an experiment, in the same way that we do CSOCs, you must know, for experiments, control. What is control? That's my baseline. You'll know this from my previous video. Remember that control groups are either literally like a placebo group or a group that doesn't receive a particular treatment, or controls are exciting because they can show up as the very people that you bring in, right? So even if you only take volunteers, for your experiment who happen to have a particular quality that's important to the study, that could be your control. Like when we talked about the people who were medically obese for that particular study, that was the control, was that they were all medically obese, and that was their starting point. There was a rack of lamb example as well that went that way, or it was like a lamb shank, because you can't not cook the lamb shank. So we were testing different temperatures of cooking various seasoned lamb shanks. And the idea was the control group was the fact that, all the things that were being cooked were lamb shanks. Okay, so that's how control shows up. We also have randomization. We've gone over this ad nauseum, but I will go over it again because I love randomization. Randomization is one of the most important things, if not the most important thing. And the key here is it limits bias. Yes, it does. And randomization is the reason that we can prove causation in an experiment, okay? Remember that we're not dealing with observational studies right now. So randomization, that's part 2. Part 3, replication. That's the fact that we have many people that we are studying this on, right? We don't do a sample of one person. We don't run an experiment on 3 people. We run an experiment on groups of people. Even if we do matched pairs, we do many matched pairs. We do several, at least, matched pairs, which you should go over in your notes as well. Make sure you understand blocking and matched pairs for experiments. But of course, that video is up. And replication just ensures that the generalizability is there and that you're not just getting a sort of blip on the map, right? And then, of course, we have comparison. That's normally between treatments or between treatments and control. And of course, that's important because we need to make the comparison to see, what went differently between this group or that group, and what does that show me? What is the causational assessment I can make, even if it's not generalizable? And then our sometimes why, as we've called it, is blocking. It's like the 5th one that's unofficial because not every study is blocked. But if there is blocking, we have subgroups in the experiment. And the beauty of blocking is that it decreases variability. This is super important. You should know what that means. It decreases variability because we've sorted people based on a particular second variable, and that means that they are in their subgroups and there should be less variance in those groups, and then we can weigh those groups and get a more representative sample. So it's more representative. Oh, you can hear my buddy yawning. And then on top of that, on top of decreasing variability and making our group more representative, it does everybody's favorite thing, right? When you block, you set it up in such a way that now we have a more representative sample, and our subgroups do not mess with any other subgroups, and we limit confounding variables. And if there's one thing Mr. Mays loves, it's to limit confounding variables. Okay, we've gone through our 4 aspects of experimentation. Let's put a bar here. Know what to generalize to. I went over this briefly. Remember that with a lot of experiments in particular, generalizing is low. And the reason that generalization is often very low in experimental studies is because we often have volunteers. Now, that cannot be the case in some situations, but most of the time we have volunteers. And that's why we have to randomize treatment groups for experiments. Now, that means that the studies we do that are experimental studies are not very generalizable. They are normally only applicable to the sample, right? Often only applicable. Oh, get my eye in there, applicable to the sample. And because they're only applicable to the sample, they are not often applicable to the greater population. But, as we said before, they do have causality. Right? And once we have causality established, then we can go on and do other cool things. Generalizing, on the other hand, when we're messing about with something lovely like sampling, right? And surveys, which you will note for your bias situation, I had you do a sampling method, and I had you do it for a survey. And that's because those are often higher on our generalizing. As long as we are random, and as long as we use some kind of method that ensures everybody's favorite thing. And what is everybody's favorite thing? Yes, of course, representation, representative. And that's what we need. We need it to be representative and random, and then we can generalize our survey results. And we talked about this on probably the first day of notes, right? You can only generalize it to the greater population that sits within the sample that you toyed with. So for example, if I only interviewed sewer rats from New York in my sampling, and I did my job and I split the sewer rats up based on various strata, what am I still generalizing my results for? I don't care about the subgroups. I don't care about anything. I only care about sewer rats of New York, right? And Mr. Mays, you can say this to me in my face. Sewer rats of New York are my people. Now, of course, I'm joking about that. Sorry, you can hear my son. He's like sucking on his binky. Okay, sewer rats of New York for the win. No, I'm just kidding. But if that's what I studied in my sample group, that is the only thing I can generalize my greater results to. Okay, we know about generalizing. We went over response versus selection bias, which I wanted to make sure I went over with you. Make sure, and this is a pullback to Unit 1 tips for a moment, make sure you know the equation Z equals data point minus the mean divided by standard deviation. But also, and do not forget this, remember that if you solve this out, your data point is also actually equal to your z-score times your standard deviation plus your mean. And we did have a question like this on the Unit 1 exam, and I guarantee you are going to see something like this on this Unit 1 and 2 combined exam. Okay, you should both know how to do this and you should know why this works. Okay, super important. Okay, remember also that z-score is not always written as your z-score is blah. It is sometimes written as like 1.42 standard deviations from, not exactly 1.42, but I'm giving you an example. Blank number, standard deviations from the mean. And that literally in math terms translates to whatever number is my z-score times the standard deviations from added to the mean. Okay? Know this. Do not fail me and mistake yourself on this. And always remember, just like on the Unit 1 exam, we had a lot of hiccups on this. Remember that for this equation, you gotta put a z-score here. Do not put a percentile here, ever. Make sure you find the correct percentile if the percentile is what's given in the question. Remember, if I say over values that are higher than a particular percent, you want to do 100 minus that percent, or 1 minus that decimal. and then turn it into a z-score, right? Always, always using invert norm. Make sure you know norm CDF and invert norm and how to apply them, and make sure you write them out if you should have an FRQ where you have to write out your work. Okay, so I'll actually write that down. Inv norm, make sure you know that, and normal CDF. These will be very important as the year goes on as well. So those will be stars for us. And if you forget how to use those, go back through a previous video and I go through that in depth. Okay. Remember also from Unit 1, and this is my hopefully my last little Unit 1 tip. I might have one or two left, but I think my last Unit 1 tip that I want you to not lose is remember that when we're doing adjustments, translations, which you should go over briefly because I'm definitely going to throw something about translations on this combined exam. Remember that measures of center, specifically like the mean, you both add and subtract to and from those, and you multiply, divide. On the other hand, measures of spread, like, I don't know, standard deviation, and don't forget the symbols, sad blueberry, right? And then mean is, of course, this funny looking U, okay? Standard deviation is only impacted by multiplying and dividing. Do not forget that. There were actually a ton of people who got this question wrong on the unit exam. Go back to the one. I know you know which one I'm talking about, where I give you a multiple choice question. You have to run it through. Don't mix this up. Only make sure you impact the mean with adding, subtracting, and multiplying, dividing. But the spread or standard deviation should only be impacted by multiplying, dividing, not adding, subtracting. I guarantee you that's coming back on the unit 2 and 1 combined exam. Make sure you know, absolutely, without question, what a parameter is. We're back to Unit 2 stuff. Parameter. This ties in well, though, because parameters are often means. They can be medians also. It is the metric, or number, of value in our experiments. Okay? So your parameter for an experiment or for a sampling exercise, whatever it is the measurement that interests you. What is the mean income level in the area? What is the average number of push-ups a human being can do? Whatever that is, that's your parameter, both in your experiments and in your sampling pursuits. Okay, I said this already, but I want to kick it home one last time. We have volunteers for the most part in experiments. Do not say that we can generalize our results from volunteers in an experiment to the broader group. If I did an experiment on, like, I don't know, a bunch of trees in my neighborhood, I could not generalize my results to trees in my neighborhood. Why? Because I picked the trees, and if I did not sample them effectively, I'm in trouble. Now, if I was awesome and I used some kind of powerful sampling method to determine which trees I would sample and which trees I wouldn't, now I'm employing sampling procedure and I might have a better shot. But if the trees magically volunteered because they could walk, like the ones in Lord of the Rings, we're in trouble. We normally have volunteers for experiments, and because of that, we actually can't generalize a lot of the time. That's why we also, like I said, randomize to treatment and control groups. But be aware, the value of experiments very often, because they're often volunteer-based, is to show causality, not necessarily to say, and this causality applies to this big, greater public. But be aware of that, and do ask me any questions on this front if this still flummoxes you. It's very important, and I guarantee you that you will see questions about this on my FRQ section in particular, but definitely on my multiple choice as well for the exam. Okay, you know this, I know this, everybody knows this. You need to know how to explain simple random sampling. You gotta know it. We've gone over it like 15 different times, not actually. We've gone over it maybe 2 or 3 different times, but we've gone over it in such a way, I hope that it's been very clear. Right? Remember the key steps. We did it for multiple ones, including the Frappy, so review your Frappy answers if you need to. It's normally assigning a number, right? Assign numbers, 1, 2, whatever your highest is. I'll call that my max, right? And then random number generator, right? Random int or rand number generator, whatever you want to say. And then you want to make sure you take however many, right? Whatever you need to sample, number sampled. Oh no. The little guy dropped his binky. He's joining us. He's feeling the wrath of applied statistics. Okay, the number that you want sampled, of course. Make sure you talk about repeats, that you will rerun them for repeats. Run them back through for repeats and make sure that there are no repeating randomly assigned numbers, but you put them back in the proverbial hat, right? You still want to be running with the same number of possible values achieved. Okay? And then you have to make sure that you then say, I assign the ones chosen to treatment, or I assign the ones chosen to control, or some other metric, whatever it is, and then the others must go to the other spot. Make sure you name both, treatment and control, or if there's no control, treatment and treatments. Yes, I know, buddy. You're excited too. We're both so excited about simple random sampling for you. Excuse me. All right. That's that. And then, of course, make sure you understand why we do each one of these sampling methods, right? Why do we do SRS? Well, because it's the best one. When do we do systematic? We do systematic when we don't have a master list of names. And it still works. Why do we do stratified? Well, you should know that. That's when there's an extra variable that concerns us. We must do stratified when there's an extra variable. I feel like my little guy's learning alongside us. And then, of course, when do we do cluster? We do cluster for ease and when we can afford to do cluster, right? When we feel that the part reps the whole. Yes, good job, buddy. And that's super important. When we feel that the part reps the whole, then we can afford to do cluster random sampling. All right, and I'll just end with this. Be very, 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 very clear about your answers. Be creative in the sections where I'm asking you to go through and be specific, okay? Give your answer. It may move in this direction or that direction for the FRQs, mind you. Show your work, okay? And walk me through your experience and your ideas. Make sure you know your stuff inside out and backwards and in such a way that you can apply them. Use critical thought. Be inventive. Be clever. I'm so proud of you. I cannot wait to see what you do with all of this information. We've gone through every little pro tip that you could possibly hope for my unit exam. I know you will kill it, but show it to me. Put the work in. We have begun a brilliant pursuit this year. We have taken ourselves from very little statistical knowledge to an immensity of it in only about a month or so. And we're about to go even beyond that. I believe in you. I'm proud of you. Thank you for being my student. This is Mr. Mays signing off with Mom.